Well, good morning. I see that I'm running a little bit over time. Let's see if I will make it. This project, as you can see, is still in prep. It has been working on it for almost 2 years together with Andrea Kunder and Andreas Koch-Hansen, who are unfortunately not here. And I'm trying to study the Milky Way bar using old population standard candles. So the Milky Way bar is a quite prominent structure, composed mainly or only of stars. Approximately half or 1/3 of its stellar mass is like in the half of the stellar mass of the galactic bulge is deposited in this galactic bar. It severely affects its surroundings, particularly the stellar streams in the Milky Way halo, and it funnels the gas toward the central regions, and it contributes to the formation of the nuclear stellar disk. And as you can see it here on this is sort of like artistic impression, and we are trying to trace this Milky Way bar using standard candles. In the past, we've quite successfully, people used red clump stars, where they nicely traced the inclination angle and the extent of the Milky Way bar. They measured the angle, which ranges somewhere around 25 degrees. And in the red clump stars, you can clearly see it, both spatially and kinematically. And the red clump stars, the important point here, they are intermediate age star in my part of the research. Therefore, their ages are between 2-3 gigayears until 10 gigayears. But when you try to look for old population tracers, old population standard candles, like Arollara variables that have a period luminosity metallicity relation that allows you to use them as distance indicators within the local group, that's where you start running into problems. And particularly 2 papers in the past decade contributed heavily to this field, and they both provide different kind of results. The first one is from Istvan Dekani from 2013. He used VVV data, targeted Arollara stars in the galactic bulge, and you see just like a bulk of stars that don't seem to have any extent, no tracing of the Milky Way bar. So he concluded, and his collaborators, that old population stars doesn't seem to be tracing the Milky Way bar. 2 years later, Pavel Petrukovic, using sort of a combination of the visual and infrared passbands, determined the distances toward Arollara stars in the Milky Way bulge, and found a nice tilt and sort of overdensity that follows the Milky Way bar. So these 2 papers sort of started a discussion that resulted in several studies, not all of them unfortunately mentioned here, but there are several caveats that both enters to the kinematical and spatial part of this field. On the spatial part, Milky Way bulge is a heavily reddened region with variation of the dust properties. So you have a reddening law that can vary. You have the reddenings that are quite high. For the distance determination for the Arollara stars, you have variety of absolute magnitude relations that give you the absolute magnitude from the period and from the metallicity. And you have metallicity scales for Arollara stars that are different. If you look through the literature for the past 25 years, you have different metallicity scales for Arollara stars that goes into these distance determinations. On the kinematical side, as shown by Andrea Kunder in 2020, you have a considerable amount of interloopers from the Milky Way halo. Therefore, Arollara stars that are in the Milky Way halo, where they spend most of their time, they, on their orbit, pass through the Milky Way bulge, and that's where we see them. When we look at the Milky Way bulge, approximately 25% of the Arollara stars that we see, those are the interloopers that sort of pollute the view that we have on the Arollara stars tracing the Milky Way bar. And then you need to remove these interloopers. You need to assume a certain Milky Way potential, certain mass distribution, and you need to integrate the orbits. And the amount of interloopers that you will find depends on the potential that you will choose. So it's a game with several problems that you need to sort of keep in mind. So this is where we start, basically, our study. We decided to go back completely to the beginning, recalibrate everything, both on the spatial and the kinematic part, and then add it all up into one paper for the Milky Way bulge. So we started here, and then we progressed into 2 parts. Basically, paper 1, where we try to recalibrate the distance estimation for the Arollara stars with a thought in mind to have a tailored estimation for the absolute magnitudes for the surveys that are targeting the Milky Way bulge, in particular the OGLA survey, the VVV survey, and Gaia. And these new period luminosity relations that we have gives us not just the estimates on the absolute magnitudes, but also a good handle on the errors. We have covariance matrices for all of our relations. On the kinematical side, there are certain surveys, spectroscopic surveys that target earlier stars in the Milky Way bulge. And the obvious advantage of earlier stars that they pulsate, you have period, you can connect it to the luminosity. But this pulsation leads to changes in the effective temperatures, log Gs, the observed line of sight velocities. So as the star pulsates, it contracts and expands. So that changes the observed line of sight velocity, and the pulsation motion is convolved with the systemic velocity motion. So you need to sort of separate those two things using line of sight velocity templates and scaling relations. And that's what we basically did in our paper too. We focus on the surveys that target the Milky Way bulge, and for those, we sort of calibrated these approaches for the nearby solar neighborhood. Now, for the actual bulge work, as I said in previous slide, we are using the optical gravitational lensing experiment, and there identified earlier stars. We are using VVV photometry to have a good handle on the extinction and the reddening, to have a good reliable distances. We have Gaia promotions, because we are trying to not just have the spatial distribution, but also know about the kinematics. And we have photometric metallicity that come from the shape of the light curves, which enter in the distance estimation. On the spectroscopy side, we have a BRAVA earlier survey, which targets roughly 3,000 earlier stars in the galactic bulge below the galactic plane, and it focuses on the calcium triplet. For the apogee provides around 6,000 earlier stars observed in the H band, both and above and below the galactic plane. And using the approach that I outlined here in the paper too, we are able to determine the systemic velocity, the motion in the space. So let's step to the distances. For each an individual earlier star in our dataset, we decided to use our own reddening maps that we derive based on the color excesses that we determined for each star. So we don't rely on any external extinction map, but I would like to compare my values. We used calibrated period luminosity relations and observed apparent magnitudes, and we have color excess for all the points that you see here. This is basically a VVV footprint for the Milky Way bulge. For these points, we calibrate the reddening law, we propagate all of the errors throughout, so we have a sort of a good understanding what is the error on each individual distance for each individual earlier star. And we do it for all combinations of passbands that we have. So basically going from visual to the K-band. Here is a comparison of the distances that we determined. The top 3 panels represents the distances derived in our study, and the bottom 3 panels represents the distances derived in the previous work. If I look more on the infrared part, the E, J minus K, and I minus K, that's where you see this kind of like a bulk, and the red point's supposed to represent the ending points of the Milky Way bar. So if you just imagine, I didn't want to draw it there, it's kind of like a line, that's where you should see the tilt, the angle for the Milky Way bar. And in the infrared passbands and the partially infrared passband, we don't see that. But once I go to the visual, I start seeing the sort of a tilt. There's this like a mild inclination angle, and I also start seeing these little, like a substructures. I call them spikes, which I can also sometimes see when I use the data from, or the approach to distance determination from Pavel Petrukovic work from 2015. When I look at the Molnar 2022, which use infrared data, I see just mostly a bulk of points, not any specific tilt with the Milky Way bar. And when I combine the distances from Molnar with the stars from Petrukovic, I see again just a bulk, no tilt with the Milky Way bar. I actually explored why I see it in the visual and not in the infrared, and what seems to be the reason behind this is that you have a variation in the extinction law toward the Milky Way bulge. Especially in these parts, you have a reddening law that changes, and especially in the V minus I, the reddening is so severe that it starts affecting the distances that you determine. You have that variation in the extinction law also in the J minus K, but it's much less pronounced, and also the J minus K color excess is much lower, so it affects the distances that you have, but not as severely as on the visual side. We looked on the spatial data, and in particular on the metal-rich stars in our data set, that could potentially trace the Milky Way bar. Basically, the peak of the metallicity distribution for our stars is at minus 1.4, and we looked at the most metal-rich end at minus 0.6. And we found this like a small tilt around 16 degrees that sort of represents the Milky Way bar as we see it in our data. It's not at 25 degrees as measured by the red clump stars, but it's at least something that resembles in the data in the spatial coordinates the Milky Way bar. Looking at the first part of the kinematical study is that we calculate the transverse velocities for our stars. Again, looking at the metal-rich part of our data set, we calculated the tangential velocities in the galactic latitude and longitude, and the dashed line represents a rotation pattern as traced by red clump stars from Sanders and collaborators 2019. And you see the red points, sort of representing the metal-rich population in our data set, follow quite nicely this rotation pattern, while the rest of the sample seems to be lagging behind this rotation. This is something that has been observed in 5D, but also in the 6D, and I will get to that in a minute. If you look at the dispersion, you see slightly higher dispersion than it was expected from the red clump stars. You see that basically all of the points on the metal-rich side, they fall above the dispersion distribution from the red clump stars. And my belief here is that what we see here is a roll of the Milky Way disk, where we have interloopers that pass our line of sight over the galactic bulge. They contribute to the higher dispersion in the galactic longitude, and we basically consider them as a metal-rich aerolar population toward the bulge, and we cannot really separate them because we are missing that one component, and that is the line of sight velocities. What you see here is our data set for which we have that one missing component. We have approximately 7,000 aerolar stars with systemic velocities, distances, photometric metallicities, proportions, and we can do orbits for these stars. For the first time, we are actually going above the galactic plane. The first thing that we did, we estimated the orbits. We chose a Milky Way potential that was originally introduced by Portail and collaborators back in 2017 and implemented in Agama software by Sormani 2022. The sort of the separation between the Milky Way halo stars or interlooper stars and the galactic bulge aerolar stars we set at 3.5 kiloparsecs. So basically, the star that exceeds this distance from the galactic center above the 3.5 kiloparsecs, that's the star that we consider as an interlooper, either a disk aerolar star or halo aerolar star. Those stars we don't consider in our study to search for the rotation. So approximately 20% of our aerolar stars we consider as a halo interloopers. There are literature estimates that range between 25 to 50% about the interloopers. But these studies use a different representation of the Milky Way potential in their orbit integration. They have a different coverage on the sky. So a lot of these things actually enter in this estimation of the interloopers. Looking a little bit closer at the interloopers and their metallicity distribution, you see basically on the metal poor end and on the metal rich end, that's where we have the most interloopers. On the metal-rich end, we have a lot of disk aerolar stars that don't have that much excursion from the plane. They don't deviate on their orbit from the plane that much. On the metal-poor end, we have a lot of halo stars, halo interloopers. If you look at their distribution in the galactocentric radii, the further you get from the Milky Way galactic center, that's where you will get the most amount of interloopers. And at some point, they even exceed the bulge population. So that's basically the reason why our number for the interloopers doesn't agree with the previous numbers. Because we cover slightly different region of the bulge, we have a different potential, and in some further cases from the galactic center, that's where we have a lot of contamination. And this is a sort of a rotation distribution for our aerolar stars in different metallicity bins. The most metal-rich bin between 0 and -1, that's where we have more sign of the rotation with the Milky Way bar. The dashed line again represents, it's a model from Yun Tai-shen from 2010, which is based on a Brava set on red giants from a similar epoch. So metal-rich population seems to follow the Milky Way bar. Once we go to the intermediate metallicity regime between -1 to -1.75, that's where we see this kind of like a lag behind the rotation here. And once we go to the more metal poor part, that's where we don't see the rotation. It's nearly flat. That's where sort of a rotation disappears, and we see a large effect of the interloopers that once we remove them, which is the red points, the whole dispersion falls down because we remove the most velocity stars, which are probably from the halo. So as I said, this is work in progress. So right now where we stand, on the metal-rich side, that's where we see the rotation, that's where we see the spatial distribution of the Milky Way bar in the earlier stars. But once we move to the metal-poor earlier stars, that's where we see a lag behind the rotation. And there is probably a mixture of those stars that follow the bar and those that do not. But that's for me to investigate more. Thank you for your attention.